Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for populating the next right pointers in a tree node. Let's look at the problem description. We are given a binary tree. Each node has a value pointer to the left child and pointer to the right child, and also the pointer to the next node in the same level. So initially the next pointer is null for all the nodes. We have to populate this next pointer such that it is pointing to the next node in the same level. Let's take a look at the example one. So in this tree 1, 2, 3, 4, 5, 7. So the next pointer of this node will be null because there is no node to its right. So when we go to the level 1, there are two nodes in the level 1. For node 2's next pointer points to node 3, and then 3's next pointer will be null because there is no other right node. So basically if we follow the next pointer, we traverse the nodes in the particular level. And for the node 4, the next pointer points to 5, and the node 5 points to node 7, and the node 7's next pointer will be null. So that's why we can see 1 null, 2, 3 null, 4, 5, 7 null. The number of nodes in the tree is in the range from 0 to 6000, and the values of each node will be from -100 to 100. So it says you may only use constant space. The recursive approach is fine. You may assume implicit stack space does not count as extra space for this problem. Let's look at the approach to solve this problem. So the given input tree is 1, 2, 3, 4, 5. So the expected output is 1 null, 2, 3 null, 4, 5 null. So we can do a breadth first traversal on this binary tree. Okay. Whenever we process a particular level of nodes, we initialize the previous pointer to null. As we process each node in the level, we update the previous nodes next will point to the current node. So that way, whenever a level is processed, the nodes in that levels are linked through that next pointer. So that's what I have listed here. Do the breadth first traversal on the binary tree. Initialize the previous pointer before processing the nodes in the particular level. As each node is processed, if the previous pointer is not null, then we make the previous pointers next pointing to the current node. Update the previous pointer to the current node. Let's look at the flowchart. Input for this procedure is pointer to the root node. First, we check whether the root node is null. If so, we return. Otherwise, we initialize the queue and add the root nodes to that queue. Then in the outer loop, we check whether the queue is not empty. If it is empty, then we return. Otherwise, we initialize the previous pointer and initialize the count variable. So basically the count will be the number of nodes in the queue at that moment, and the previous will be initialized to null. Then the inner loop will process all the count number of nodes in the queue at that point. So we keep track of count. If it is 0, then we break out of the loop and go ahead and process the next level nodes. Otherwise, we dequeue the first element in the queue and assign that to the current variable. Then we check whether the previous pointer is null or not. If it is null, then we don't have to update the next pointer of that previous node. Otherwise, we have to update the next pointer of the previous node to point to the current node. Then we check whether the current node has a left child. If so, add that left child to the queue. If it has the right child, add that right child to the queue. Then at the end of the inner loop iteration, we have to update the previous pointer so that it points to the current node. And we decrement the count variable. Once all the nodes in the current level is processed, then we break out of the inner loop and process the next level nodes. once the queue is empty, that means we processed all the nodes in the tree and we return the root node at the end. Let's move on to coding. First I check the root node is null or not. If it is null, I return. Otherwise, I initialize the queue with the root node as the first element. Next I write the outer for loop. This loop makes sure all the nodes in the tree is processed. So every time I check whether there is an element in the queue. If so, those elements will be processed level by level. First I initialize the previous pointer, then get the current number of elements in the queue and assign that to count. So then if the current level, the count number of elements is present. So the inner for loop will process those count number of elements. So I check the count greater than 0 as the condition. And inside the inner loop, I dequeue the first element in the queue and assign that to current pointer and then update the queue. Then I check whether the previous pointer is not equal to null. If so, I make the previous pointer's next point to the current node. Then I check whether the current node has the left child. If so, I add the left child to the queue. Then I check whether the current node has a right child. If so, I add that right child to the queue. Next, I update the previous pointer to point to the current node, and then I decrement the count. And finally, I return the root node. Next, I am going to run the test cases. Okay, there is compilation error. Okay, let me rerun the test case. Okay, all the tests passed. Next, I am going to submit this program. Cool, this program is accepted. Next, I am going to do the code walkthrough with sample input. Let's do the code walkthrough for this input. So we have the binary tree 1, 2, 3, 4, 5. So the expected output is 1 null, 2, 3 null, 4, 5 null. Okay. So first, when we call the connect function, first we check whether the root is null. If it is null, then we return immediately. Otherwise, we initialize the queue with the root node as the first element. Then we enter the outer loop. There we check whether the queue has some elements in it. In this case, there is one element present in the queue, and we initialize the previous pointer for each iteration of the outer loop. Okay. Then we get the length of the queue and assign to the count variable. So we see count equal to 1 and the previous is null. Then we enter the inner loop where we dequeue the first element in the queue and then update the queue. So the current will be 1 and we update the queue. So at that time the queue will be empty. Then we check whether the previous is not equal to null. If so, we update the next pointer of the previous node to point to the current node. So in this case the previous is null, so we do not update the next pointer. Then we check whether the current node has the left and right child. If so, we add those children to the queue. So we see 2, 3 because they are children of the current node 1. Okay. After that we update the previous pointer to point to the current node so that the next iteration will have the current node as the previous node. And then we decrement the count. So the count becomes 0. So once it becomes 0, then we break out of the inner loop. Then we process the node present in the next level, that is level 1. Okay. So when we enter the outer loop iteration 1, again we initialize the previous pointer to null, and we get the current number of elements in the queue, so which is 2. Then we enter the inner loop. So in the inner loop we dequeue the element and assign to the current, and we check whether the previous is not equal to null. In this case it is null, so we are not updating the next pointer of the previous node. And then we check whether there is a left child present. In this case 4 is the left child, so we add that to the queue. We check whether there is a right child present in this node, but here there is no right child, so we are not adding anything. Then we update the previous pointer to point to the current node. So we see the node 2 as the previous node, and we update the we decrement the count, so the count becomes 1. Then we enter the next iteration of the inner loop. There we at that time the queue has 3, 4, so we dequeue the node 3, and we check whether the previous is not equal to null. In this case previous pointer points to the node 2, so we update the node 2's next pointer to point to the node 3. Okay. Then we check whether there is a left child present for the node 3. There is no left child, so we are not adding the left child to the queue, but there is a right child present for this node, which is 5, so we add 5 to the queue. Okay. So when we leave the iteration 1, we have 4 and 5 in the queue, and the previous is pointing to 3, and the count is 0, so the inner loop will end, and then we enter the second iteration of the outer loop. So in the second iteration, when we enter, the queue has 4, 5, and the count is 2, and the previous pointer is initialized with null. Then we enter the inner loop, and we dequeue the first element from the queue, which is 4, and then we check whether the previous is not equal to null. In this case previous is null, so we are not updating the next pointer. And then we check whether there is a left child or right child. In this case this is a leaf node, so there is no left and right child. We are not adding any node to the queue. Then we update the previous pointer to point to node 4, and we decrement the count. So when we leave, the queue has 1 element, and the previous pointer points to 4, and the count is 1. In the next iteration, we dequeue the 5 from the queue, and we check whether the previous is not equal to null. In this case it is pointing to 4, so we update the next pointer of the 4 to point to node 5. So the node 4's next pointer points to node 5. And then we check whether there is a children for this node. There is no children, so we are not adding any node to the queue, and we update the previous to point to node 5, and then we decrement the count, which becomes 0. Because this is 0, the inner loop will end, and then when we come out, there is no element in the queue, the outer loop also ends. Then finally we return the root node. So at that point, the node 2's next pointer point to node 3 and the node 4's next pointer point to node 5. Next I'm going to do the time and space complexity analysis for this solution. Let's do the time complexity analysis for this input. This input tree has 6 nodes. Okay, so in order to update the next pointer of all these 6 nodes, we have to traverse all of them. So for 6 nodes, we have to traverse 6 using the breadth first search. So the total number of nodes visited will be, at level 0 we visit 1 node, at level 1 we visit 2 node, at level 2 we visit 3 nodes. So totally we visit 6 nodes. So for n number of nodes, we have to traverse n nodes. So the time complexity is order of n. So the space complexity is order of 2 to the power log n, because we are using the queue. Okay, so the maximum space required for this queue is the total number of elements present in the last level. Okay, so if the binary tree is complete, then at height 0 we need space for 1 node, and at height 1 we need space for 2 nodes. So the tree with height 2 we need space for 4 nodes at the most. So for the tree with height h, we need 2 to the power h nodes, where h is the log n base 2. So the space requirement while we are doing this breadth-first traversal is 2 to the power log n. So the space complexity for this solution is order of 2 to the power log n. Thanks for watching this video. Have a great day.